Welcome to Kubernetes Security the Easy Way. My name's Aaron Small, and also today we'll have Greg and CJ, software engineers on the GKE security team. Ostensibly, we're here to talk about GKE security, but really this talk is about trust. When you choose GKE or any cloud provider to host your product, you're placing your trust in them, in us. I don't know about you, but I can't open the news without reading some headline about information security, some cyber attack, or the latest breach of sensitive information, which, to those people impacted, is just one more breach of trust. Software security is something we all have to care about today. But to many, it can feel like a distraction from doing what's most important, which is building your product and delighting your customers. We're passionate about software security. We get up every day delighted by the prospect of finding that vulnerability before the bad guys do and building the tools people can use to build state-of-the-art secure applications. There are lots of talks and blogs and white papers you can read that'll talk about how to harden your Kubernetes cluster, talk about common attacks, or highlight recent compromises. This talk is not about that. Like I said, this talk is about trust. And in my experience, the best way to build trust is to be transparent. So we're giving you a backstage pass into the work we do at Google, behind the scenes, under embargoes, and even before you build your first container, to keep your cluster as secure as possible. For those of you who are familiar with GKE, it's not unlikely that you think of it as simply a managed Kubernetes control plane, and you might infer from that the security we provide stops there. While we do take control plane security quite seriously, that's not the end of it. Greg and CJ will discuss how we secure your GKE nodes, the control plane, and the tools that we've built that you have at your disposal for attack detection and vulnerability mitigation. CJ also has a demo that'll demonstrate a potential compromise scenario and how the tools we've built make it easy to respond and mitigate. Okay, most of you have probably seen a diagram like this before, so please forgive the early morning GKE 101. I do want to give a little bit of groundwork, though, for the rest of the presentation. GKE, in its simplest terms, is a hosted Kubernetes control plane and some number of Kubernetes nodes. You, the developers and administrators, interact with the control plane, and your users interact with the containers that you've deployed on the nodes. The control plane manages your workloads. It manages what nodes belong to the cluster, and the certificate authority that handles authentication of the node agents, also called kubelets. The nodes themselves execute containers, receive configuration data, secrets, etc., that they need to function from the control plane. It's on those nodes where the aforementioned hardening guides and best practices come into play. As you get more familiar with Kubernetes, you'll customize this and configure it and really make it your own. It can get as complex and as unique as you want to make it. The security of this space follows the shared responsibility model, meaning we're responsible for the security of the infrastructure itself, and you're responsible for what you deploy there. You manage, among other things, the node specification, which has all the standard VM knobs you might expect, number of cores, amount of RAM, the operating system, whether or not there's a GPU attached, what services and workloads you've deployed there, and any Google Cloud Service accounts that you use to talk to other Google Cloud services. But today, we're talking about what Google does for you. So with that, I want to hand off to Greg, who's going to discuss node security.
Thanks, Aaron. So I'm going to start out the behind-the-scenes tour talking about node security. And I'm going to build this picture up in a few different layers. So we're going to start at the VM provisioning layer. There's been a number of other Google talks in the past about the great security work Google's doing below that layer, things like hardware and firmware security. I'm going to skip that in favor of kind of covering new material and making sure we get to Kubernetes stuff. So starting at the virtual machine layer, then the operating system on top, then the kubelet and how we bootstrap the trust in that system, and finally the system containers that make up Kubernetes and other Google containers that we run. So starting at the VM provisioning layer. So when you create a cluster with GKE, you get nodes that are automatically provisioned into a virtual private cloud. We create a firewall that has just enough privilege for the control plane to be able to talk to the nodes and the nodes to be able to talk to each other. The VMs have disks that are encrypted at rest. You can read all about that at this link here. And they really benefit from a lot of work that Google's done over the years to harden our hypervisor. So Google has spent a large amount of security time making sure that VMs running on that same shared hardware are really well isolated from each other. And our VMs inherit all that great work that Google's done previously. As an optional feature at the moment, it's currently beta. You can make when you create a cluster, you can make it a private cluster. And that means that you essentially take it off the public internet. So your nodes get private IP addresses, RFC 1918 addresses. And whenever you do that, it's a good, I think, when you don't need a service on the internet, it's always good to be able to remove it from the internet. You kind of take out a bunch of attacks related to just kind of general internet scanning. So that's the virtual machine layer. So the next layer up is the operating system. So the default operating system that we offer on GKE is the container-optimized OS. We also offer Ubuntu by Canonical, but in the interest of time today, I'm just focusing on COS. Canonical also has a great security team and builds a great OS. But I'm talking about COS today. So this is an OS that's built by Google. It's based on Chromium OS. It's a really minimal OS. It's really just enough OS to run containers and not much else. And that's good because less code means less vulnerabilities, less attack surface, less maintenance burden, less patching, and all of that stuff is good. We've also spent a significant amount of time hardening this operating system. So we've enabled a whole bunch of different kernel security features and set a bunch of secure defaults kind of at the kernel layer and various other operating system knobs. And the idea there is to make that initial execution step of any attack much harder. So if we can put in a memory protection in the kernel that makes it harder for attackers to execute, that's a win. We've also spent quite a bit of time trying to make it harder to persist through a number of different mechanisms. So things like an immutable root file system, making the root file system read-only, and having a verified boot chain means that a number of the sort of traditional ways to persist on an operating system are made much harder on COS. We're also enabling features like eBPF to allow third-party security products, particularly detection products, to run on GKE. We want those products to work well on GKE. And there's more work you can do here if you want to go the extra mile. So COS also supports SecComp and AppArmor, so you can really kind of write a very specific hardening for your particular application. If you'd like to go that far into it, you can kind of define the normal behavior of your application. And the idea there is that if an attacker is trying to operate outside the bounds of what is normal for your application, then it should be blocked by these technologies and make their life a lot harder. And you can read more about COS and all the kind of hardening and security work we're doing there at this address. And for all of these little links that I'm firing up on the screen here, I have a giant slide at the end with a big list. So if you just want to take a photo of that one, you can. I also briefly wanted to mention the team behind COS. So we have a dedicated team that is working on maintenance, testing, security patching. We also have a lot of Google in-house Linux kernel expertise. So that benefits the whole Linux ecosystem. Those people are developing new kernel security features and also finding vulnerabilities and patching them. But we're also benefiting from that expertise with COS. So we're driving features through the kernel and into COS that we're making use of. So I'll just give you a second to absorb this diagram. We're up to the next level now. So we've got VM, OS, and then on top of that is Kubernetes. So this is a fairly simplified version of how the kubelet bootstraps its trust. So I'm going to walk through this and give you an idea of kind of how that happens. So what makes a Kubernetes node? It's when you have a kubelet that's registered with the API server and can authenticate to it. So we start down the bottom of this picture with the node VM where the kubelet's running, and it retrieves a bootstrap key from the metadata server, which is running outside the VM but beside it. So it retrieves that key and then creates a certificate signing request. It's a standard X509 certificate signing request and sends that to the API server. The API server receives that CSR and checks that it's authenticated with that bootstrap key. It does some other checks on the CSR itself, and then it sends it off via a webhook to a signing API, and that's actually running outside the cluster. So that hosted control plane is running on a GCE VM, and the Google prod box is, you may have heard of Borg, our internal infrastructure. So that signing APIs and keys are held externally, so that call goes out to that API, the certificate request gets signed, and the cert propagates back to the kubelet. The interesting part of all of this is that the signing keys are actually held externally to the cluster, so we have an extra trust boundary in between those two. So properties of this procedure: the traffic's all authenticated and encrypted, the trust comes from the virtual machine. We end up with a per node X509 identity, which is actually really important. CJ will talk later about how this is useful in control plane security with the node authorizer. I mentioned the CA is off the cluster. And in the future, we're looking at how we can improve this bootstrapping process. In Kubernetes 1.11, where my team contributed some code that will allow the kubelet to bootstrap itself using a trusted platform module. And the idea there is that the kubelet will no longer have to handle the key material directly. So that will be a security win. So once we have a kubelet, that isn't all that we need for the cluster. There's a bunch of other cluster services that need to run. So there's Kubernetes things like kubeproxy, cluster DNS, and there's also Google extra add-ons like logging containers, monitoring containers, as well as things like the container runtime. So Google does a lot of work to maintain these, make sure they're working, make sure they work with the control plane, make sure they scale appropriately. But the security relevant pieces are that we deliver these in a defensible configuration, that you won't find things like a container runtime port listening on the open internet, for example. We also look at the security of all these containers regularly, so we're scanning the containers referenced in the Kubernetes source code for vulnerabilities, and we're patching those where patches are missing. So that's kind of what we do with those containers. There's actually some work here for you, the GKE user, to do with these containers as well. So you really need to be able to upgrade your nodes to get those patches. So I just talked about the security patching process. Essentially how that works is we will patch the container, release a new version of the container, and then update Kubernetes to reference that new version of the container. And when we do that, we'll bump the node version. So a node upgrade is essentially the rising tide that lifts the container ship that has all the containers on it. So to make that process easier, there's actually an auto upgrade feature that you can opt into. So you can say, Google, please handle the upgrades of these nodes automatically. I don't want to think about it. And to give you some control over when that happens, you can actually specify a maintenance window. So that's a 4-hour window that says to Google, hey, please do your maintenance tasks within this window. So that's node security. We talked about VM provisioning in terms of hypervisor, firewalls, the operating system, kernel hardening, security patching, Kubernetes trust bootstrap in terms of how the CA works, and the system containers and how they're patched and upgraded. The takeaway I'd like you to take from this section is that Google's doing a whole bunch of work here so that you don't have to care about any of this, and you can focus on your application. But the one thing you do need to do is look after your node upgrades. So I'm going to hand it over to CJ to talk about control plane security.
Thanks, Greg. So Greg gave us a good overview of what GKE provides you in terms of the managed node environment. But a lot of what you think of the security that GKE provides you is the managed Kubernetes control plane. So on GKE, each cluster control plane is separated by a VM boundary from every other cluster control plane. So that means that the API server that you talk to is entirely yours. The etcd database that houses your Kubernetes API resources is all yours. And then the add-ons that run in your cluster are all yours. The Kubernetes API that you talk to is the same Kubernetes that you would get running it yourself, but on GKE, that's all managed by Google. So a big part of that isolation is the per cluster certificate authority. Greg mentioned it. It governs the node credentials that the node agents use to authenticate to the managed control plane. It also governs the server-side credentials that the managed control plane authenticates itself with. The key for that, as Greg mentioned, is held off the cluster for defense in depth, encrypted at rest. The fact that it is a per cluster CA means that we get a simplified chain of trust. We don't depend on a public CA or PKI for this to work. And then that key is rotatable on demand, either just for good hygiene or as part of an incident response. So Greg mentioned the per node identity that you get as part of that kubelet trust bootstrap. And that per node identity becomes super important when we start thinking about how nodes interact with the managed control plane to manage what workloads they're actually running. So node agents have only the permissions they need to do their job. So that means that one node is only allowed to update status about itself, and it's only allowed to see things like secrets and config maps that are actually pertinent to the workloads that are scheduled onto it. And this is just another defense in depth step that helps make a compromise of one node stay limited to just that node. So another huge benefit you get from the managed control plane that GKE gives you is the seamless authentication with the same user accounts that you already have on Google Cloud. So whether you are taking a look at usage or digging through logs in the Cloud Console, or you're on the command line debugging your Kubernetes application using gcloud and kubecontrol, you're the same user with the same strong authentication that you get anywhere else from Google Cloud. Building on top of that authentication story, GKE is integrated with Google IAM, which gives you the ability to manage the permissions, grant your team just the permissions they need to do their job, and then see and enforce that policy in one place across your entire organization. For advanced Kubernetes users, this all plays nice with Kubernetes RBAC for access control. So now that you know who is supposed to be able to do what, it's still really helpful to have that audit trail after the fact to see what actually happened. So the pertinent info you want on GKE is what has accessed the Kubernetes API, and also what operations have taken place on the underlying GKE clusters. So if you've ever been in a situation where you had an incident and then you looked after the fact just to realize that you forgot to turn on logs, well, on GCP, we give you 400 days of retention of what we call admin activity logs by default. So that's mutating operations. So on GKE, that's things like creating new Kubernetes pods or upgrading the version of your GKE nodes. For everything else, for things like read access to the Kubernetes API, you can enable data access logs, and those get retained for 30 days. Those get ingested directly to Stackdriver, where you can analyze them there. If you have another tool that you like to analyze your logs with, you can easily export logs from Stackdriver using something like Cloud PubSub. So to show off how powerful all of these features can be together, I'm going to set up a little demo scenario. So we're going to say that we have this continuous integration, continuous deployment system that every hour it's going to build a new version of our application, and it's going to then push that application artifacts up to Google Cloud Storage. And then once that's done, we're going to deploy the new version of our application out to our GKE cluster for some testing. So that's all good. We've got that running. And then one day we get the dreaded email. Google has detected that some credential from our project appears to have been exposed somewhere on the public internet. We dig back a little bit, and sure enough, we accidentally checked in our private key to a public source control repo. So what that means is that the deploy piece of this CI/CD system we set up is now using a credential that has access to a GKE cluster, and that credential may be exposed somewhere. So how would we respond to this? So let's pop over to the Cloud Console and walk through some of our options. So the first thing you would want to do in this scenario is pop into the IAM Service Accounts tab and rotate that key. And you do that just by coming over here to create a new key, provision that out to the system that needs it so that you can take this without any downtime. And then you delete the key that we saw was compromised. I'm not going to do that yet. For the sake of demonstration, we're actually going to walk through what could have happened in this situation. So the next thing we want to take a look at is what permissions did that service account actually have? So if we go into the Permissions tab, we can see that our CI/CD pipeline service account here, we granted it the CI/CD pipeline role. And now what that is actually an IAM custom role. So if I pop over to the Custom Roles tab, you'll be able to see where I defined this CI/CD pipeline role. And clicking into that, we see that the only two permissions contained in that role are the ability to get deployments and the ability to update deployments. We have a very simplified CI/CD system. All it's doing is updating the container version to point to the new application we just built. Now, deployments.update is still a fairly elevated permission. It allows you, like I just mentioned, to change the container image or to even change parameters or the environment that your application is running in. So we're not completely out of the woods yet, but by limiting these permissions to exactly what this thing needs to get its job done, we've at least limited the surface area of the potential attack. So now that we've seen what this thing could do, let's go ahead and take a look at what it has done. So if we pop over to the stack driver logs, and we look at the Kubernetes logs, we see it's fairly noisy. The Kubernetes API is a pretty noisy place. There's a lot of activity going on. Luckily, in this stack driver UI, we can easily filter this by a text search. We know our service account had CI/CD in it. And we see that the thing that's happened so far is mostly what we expect. It's our hourly push to our GKE cluster. So far, so good. We can dig in here, find some interesting information in this. We can even start streaming the logs so that we see new activity as it happens. So let's switch gears a little bit and think about what this might look like from a potential attacker scenario. So a common way you might see this happen is an attacker might write a very shallow, broad script that's just scanning the internet for anything that looks like credentials. Then you might take a really quick attempt at trying to make use of those credentials, trying to make money off that probably by implanting a malicious application somewhere. So I've written up a little script that's just going to pretend to scan the internet for keys. So everything you see in white is sort of pretend stuff, but the things that are in green are actual commands, and then the things that are in red are the responses from those commands. So we're gonna scan the internet for keys, and sure enough, it came across our exposed service account key for that CI/CD pipeline. So the next thing it'll do is configure this shell to make use of those credentials. And we're going to go ahead and attempt to implant our malicious application as a Kubernetes pod in this cluster. And you'll see that luckily that request was denied. So the error we got back from Kubernetes is that we did not have enough permissions to make this request. If you remember back to the IAM custom role we took a look at, we had the ability to get deployments and update deployments, but we didn't have the ability to create pods. So that's good. So maybe this script tries to create these things a couple more times, but it's gonna fail every time. And if this is just a shallow, cheap scan, maybe it just moves on, and we were lucky that we got safe there. Now, if you were watching over here on the right, you saw these logs start to pop up. And so in this scenario, it's fairly obvious to see where the anomalous activity came in from. In other incidents, it may not be this easy. You know, we can directly see that this double exclamation point red thing got an error. We can dig into how exactly that happened. But in real incidents, you might have better luck analyzing logs further here or exporting them to a different system to do more in-depth processing. That's as easy as creating an export. You can send that to BigQuery, give it a name, create the sync. I've already done that, so let's pop over to this BigQuery tab where I've streamed logs to a BigQuery data set. I've already written out a query. I'm going to take a look for any calls that have come from this service account, but they came from outside what I'm going to pretend is our corporate IP range. We know our CI/CD system is only going to be calling from this IP range that we expect. So if we do see accesses from this service account coming from elsewhere, we'd like to know. That's unusual. And then just from that, I'm going to gather some pertinent information. So we take a look at this query, and sure enough, it's going to pop up with those 3 calls that script just made. We see from the HTTP code our attacker was unsuccessful, didn't have enough permissions, and we have the IP of the caller right here that can help inform some of our additional incident response. So I'm not going to go any deeper into incident response here. Incidents are fairly unique. I just wanted to highlight some of the tools that we've provided that help you start to begin your incident response. If you've ever been in a situation like this, you know how critical it can be to get good, solid information quickly to stakeholders and leadership. So we walked through how GKE's integration with Google Authentication gives you a single place to go manage and rotate your credentials. We saw how GKE works with IAM to grant granular least privilege permissions and set and enforce that across your org. And then lastly, we saw how GKE's automatic audit logging gives you the ability to have a solid incident response story without having to have remembered to turn it on. And with that, I'm going to hand it back over to Greg, who's going to talk through some real-life examples of vulnerability management in GKE.
Thanks, CJ. So I wanted to talk a little about vulnerability management. It's something that often doesn't get a lot of airtime. And I wanted to do that with some example case studies. Now, these case studies are just 2 examples in time. I think they're both interesting, but not every vulnerability is going to work out like this. Each vulnerability tends to be unique on a number of different axes. So with that caveat, the first one I want to talk about is some vulnerabilities that were found in some software called DNS Mask back in October in 2017. So this is open source software. It is a very well-used piece of software, not written by Google. It's open source. And it provides critical DNS services and other networking services for many, many different companies. It's very well used. It runs on laptops, desktops, servers, IoT devices, lots of different places. So I'm going to step through kind of how the vulnerability was found, how we fixed it, and what the outcome was for GKE. So how was this vulnerability found? So Google employs a bunch of really world-class security researchers internally. They are focused on finding vulnerabilities in our own products and fixing them, as well as finding vulnerabilities in critical pieces of internet infrastructure and making the internet safer. So in this case, and we also have the vulnerability rewards program where we engage the external security research community and we pay them for their work through a bug bounty program. So in this case, for DNS Mask, this was a Google-discovered vulnerability. So a Google security researcher found a whole series of vulnerabilities, actually. And if you're interested in kind of geeking out on the details of these vulnerabilities, you can go read all about them here. It's not really super relevant for this presentation, but the worst of them was a remote code execution. So the Google security researchers started working with the maintainer of DNS Mask, who's an external party, doesn't work at Google. Together, they came up with a fix that fixed the vulnerabilities that had been found, and then we started a worldwide kind of multi-company coordinated disclosure effort. It's really complicated kind of disclosures to try and get a number of as many people patched as possible. And we enlisted the help of the US CERT, the US Computer Emergency Readiness Team, with that effort. So what did this mean for GKE? So internally, we identified that GKE and Kubernetes depended on DNS Mask. And that meant that we knew we were vulnerable, and so we kicked off the Kubernetes security response process. And that starts with us emailing the Kubernetes product security team, which we actually sit on as well, too. So that's a handful of representatives from companies at Google, Microsoft, Red Hat, In this case, CJ actually led the vulnerability response, so we volunteered to take the lead. In other cases, it might be someone from Microsoft or someone from Red Hat, all very experienced security engineers with deep expertise in Kubernetes. So we took the lead on this one, which was essentially working out how to fix it in Kubernetes. So we figured out that we had to patch kubedns with this new fix that had been developed with the DNS mask maintainer, and release a new version of that container. So and once we'd gotten the fix kind of settled, we had to build and stage quite a number of releases. So the releases followed the security release process, which is extensively documented at this link. You can go read all about it. But essentially, what we were able to do was create Kubernetes releases for 3 different release branches, and even actually one more, because 1.8 was about to be released at the time. All of those contain, we were able to patch all those branches with the fix and release the fix on the same day as the public vulnerability went out. And for GKE, this meant that as part of the managed service, we were able to make a change on the masters that rolled out a change to kubedns across the clusters. And so the outcome for GKE customers was that we were able to patch this vulnerability at the public release time without any action required on the part of the customer. So I think that's kind of the ideal outcome, that Google spends a whole bunch of engineering hours figuring out how to do all this and just fixes it for everyone. And you don't even have to worry about it. You may not have even been aware of this vulnerability. It won't always work out like that, but I think that is the ideal case. The second case study I wanted to talk about briefly is the Spectre and Meltdown vulnerabilities. So this was from early January this year. So these were very interesting vulnerabilities. Probably most of the people in this room have heard about them. If you haven't, they were discovered by Google Project Zero. They were vulnerabilities in most modern CPUs. They're caused by this speculative execution feature. I'm also not going to dig into the details of this. If you do want details, there's an entire next session that has actually already happened, but you can find it on YouTube if you want to dig into how Google found these vulnerabilities and how we fixed them across the whole infrastructure. It should be a really interesting talk. There's also a blog post, and if you just Google these things, you'll find out a ton about them. They were very well known. So what did this mean for GKE? So we knew that we had to make virtual machine changes so that there was changes necessary to the hypervisor to prevent one VM accessing the host memory of the hardware machine that was running the VM and getting access to another VM on the same machine. So we needed some hypervisor changes to fix that problem. And then as a second layer of defense, we also needed some changes in the kernel, enabling some new protections there that required a new version of CAUS. So that was essentially a second layer of protection. And you'll hear Google security engineers talk about 2 layers of defense a lot. So we're always looking for 2 layers of defense where we can find them. It doesn't always happen, but our experience has told us that when we can get 2 layers of defense, that's a really good thing, and it really helps. So there was lots of testing involved, many hours of engineering time spent on getting these fixes and testing them, testing upgrade paths, testing performance in particular, because these new kernel security features had some significant performance changes. So the outcome for GKE, I think, was actually pretty cool. So we were able to live migrate using technology that GCE basically built. So we were able to take those nodes that were running customer workloads and live migrate them onto that new version of that hypervisor without any interruption. I think that's actually pretty awesome, given the scale of these vulnerabilities and how complex they were. There was still some customer work required, so that upgrade to the CAUS image did require a node upgrade, like I mentioned previously. But we were able to deliver kind of like that first defense without any customer effort required. So in general, how do we handle kind of communications for security patches and similar issues? If there's a serious security vulnerability, we'll send targeted emails if it requires some action by the customer. And for everything else, we have a security bulletins page that you can see at this link. And it has a RSS feed you can also subscribe to. All these links are at the end, too. I also briefly wanted to mention again the Google Vulnerabilities Reward Program. So we built on a lot of success with this program with Android, Chrome, and all of Google's web properties. And I just wanted to call out specifically that it does apply to GKE. This is not a new announcement. It has applied for a very long time. But this essentially gives us a force multiplier for engaging that external security research community and getting vulnerabilities, finding new vulnerabilities and fixing them as quickly as possible. So before I hand it back to Aaron, I just wanted to mention the key takeaway from that section, I think, is that Google is doing a whole bunch of work in vulnerability management to make it as easy as possible for you, the customer. It won't always be zero effort on your behalf, but we were really trying to minimize that effort that you need to put in on those kind of annoying problems with patching vulnerabilities.
OK, so I feel like we just shotgunned a lot of content to you guys, so I'm going to give a pretty brief recap. Greg discussed the layered approach that we take to GKE security, all the way from VM provisioning up to Kubernetes configuration. CJ discussed control plane security, as well as gave us a demo of how you might handle the compromise of a sensitive secret. And then Greg came back and walked us through a couple of marquee vulnerabilities over the last year or so and how we managed them. So what's the point of all of this? What message are we sending? What do we want you to take away? That's that software security is our full-time job on GKE. And we want to give to you that trustworthy infrastructure you need to build state-of-the-art, world-changing secure applications. This is one of the photo slides. We have a ton of great container security content at Next. Some of this has already happened. So it'll be available on YouTube. I would highly recommend going back and watching them. We also have several more talks today that I would definitely encourage you to go visit if you care about security. I'll be at most of them if I can. And this is the links slide that Greg referenced before. I'm glad it's big enough for you to read. Thank you. That is all the content that we have so far.